Introduction to Optimization, Questions for Screen Recording Task, Part 4, Optimization with Constraints. Question 11. Illustrate KKT conditions graphically. The problem we want to solve is finding the x such that x gives us the minimum of fx subject to gix less or equal 0, where I going from 1 to n. So, to show our problem graphically, we will assume that n equals 3. Now we can see a drawing of our problem where those lines are our constraints. This is G1, G2, and G3. Okay, this is the feasible area where all the constraints are less or equal 0, and outside the feasible area, every constraint can be greater from 0 or less or equal 0, but outside of the feasible area, not all conditions hold. So we can also see the red rings that represent the contour lines of F. So we want to find the minimum point of F that is inside the feasible area. We can see that this point is X star, which represents our optimum. And now we can also look at the direction of the gradient of F. We can see that this is the minimum, this is the minimum. So we can know that the gradient always wants to get far from the minimum point. So we know that in X star, the direction of the gradient of F is inside the feasible area because it's going far from the minimum. But we also know that G1 is negative or equals 0 in the feasible area and positive outside of the feasible area. So we know that the direction of the gradient of G1 is into the minimum point. So we get that the direction of Fx optimum plus lambda multiplied by the gradient of Gx optimum equals to 0, because they are both in opposite directions. We can also see in the direction that since all our constraints are continuous and they are going from non-positive to positive, we can see that on those lines, all our constraints equal to 0, because here they are negative, here they are positive. So because they are continuous on the line, they have to be equal to 0. Now we will show our problem with equations. So we can see that our problem is finding the minimum of fx subject to gix less or equal 0, where I is 1, 2, or 3. And now we will show the Lagrangian. The Lagrangian is fx plus lambda I gix star, but here we can see that x star only touches G1. So we know that G2 and G3 has the Lagrange multiplier of 0, and we get that the Lagrangian is fx plus lambda 1 G1 of x star. Now we can see that we want to find the minimum of the Lagrangian. So we are deriving our Lagrangian and get that the gradient of the Lagrangian is the gradient of fx star plus lambda multiplied by the gradient of G1 star. And to find the minimum, we compare it to 0. So we find that the gradient of fx star equals to the minus lambda multiplied by the gradient of G1 x star. And this corresponds to the direction we found in the drawing. Now we will show the Lagrangian in the general case. So our general problem is minimum fx subject to gix less or equal 0, where I is going from 1 to n. Our Lagrangian is fx plus sigma of all active constraints of lambda I gi x star. IA represents the active constraints, which means the constraints that our solution touches. For example, here the only active constraint is gi, but there can be more. So to find the minimum of this Lagrangian, we are going to derive it and compare to 0. So we know that the gradient of the Lagrangian equals to 0 if and only if the gradient of fx star plus sigma of all active constraints lambda I gradient gi x star equals 0. Now we want to see the necessary conditions for the KKT. So the Lagrangian of the KKT condition is the Lagrangian we saw, and we know that it equals to 0 in the feasible area where all the conditions are less or equal. Excuse me, the gradient of the Lagrangian equals to 0 in the feasible area where all constraints are less or equal 0. And we know that for active constraints, the Lagrangian multiplier is greater or equal 0. And we saw that the constraint itself equals to 0. And when the constraint is non-active, it gets a Lagrangian multiplier that equals 0. So from those constraints, we get the complementary slackness. The complementary slackness condition determines that the sum of all our Lagrangian multipliers multiplied by our constraints equal to 0. And that's because the non-active constraints get a Lagrangian multiplier of 0, and the active constraints get that they are equal to 0.